Reduction of fiber nonlinearities in 5G. Abstract: the evaluation technology of today is 5G. The 5G increases the data rate and reduces the bit error rate. The wavelength division multiplexing technique is used for transmitting more number of channels through a single fiber. In wavelength division multiplexing, WDM, system of 5G, arises nonlinearity, and the major nonlinearities that arise in fiber are FWM and SRS. We use single-mode fiber for transmission. When the optical signal is propagating through the fiber, it undergoes power loss, scattering, and bending, which results in crosstalk, power transmission, and phase modulation. Due to this, the performance of the WDM system gets degraded. In this paper, the effect of four-wave mixing, FWM, and stimulated Raman scattering, SRS, in wavelength division multiplexing, WDM, system of single-mode fiber is reduced. The reduction of FWM and SRS effects for 4 channels, 8 channels is done here to improve the efficiency of 5G. Keywords: WDM, nonlinearities, SRS, FWM, power tilt, unequal channel spacing, equal channel spacing, dispersion. Introduction. In 5G, IoT expansion is going to take place. It will generate a huge amount of data and connect several networks. The 5G provides low delay, high availability, high reliability, low jitter, and more capacity. For efficiency, fiber helps us in the backhauling of 5G. Thus fiber serves as the backbone for 5G. The optical fiber is a medium where the light source is produced via laser or LED and transmitted through glass or plastic fiber, having 2 layers called core and cladding, which differ in their refractive index, and the light is received through the photodetector and converts it to electrical signals. The fiber is divided into single and multi-mode fiber. The single-mode fiber was a single strand of glass having 8.3 micron to 10 microns of diameter. It has a narrow diameter, so one mode of propagation takes place in it. It carries higher bandwidth than multi-mode fiber, but it has to have a narrow light source for it. The wavelength used for it was 1310 nanometers and 1550 nm. The multi-mode fiber will have a diameter of 50 to 100 microns, and it is used for a very short run only. The multi-mode fiber is having a large diameter of 62.5 micron and transmits only for short distance with the light source as LED, but the single-mode fiber will transmit a narrow light source of 8 to 10 microns produced by laser for a long distance. So the single-mode fiber is used for 5G. The optical communication system will operate at a range of few milliwatts power. In fiber, wavelength division multiplexing system is implemented as it does not pose any real problems like traffic and data rate. WDM provides much better latency. WDM has the efficiency of transporting a large amount of data in single fiber by separating them with a unique wavelength. WDM, as the data rate increases, the time decreases. There are other systems like TDM, PDM, etc. The WDM will increase the capacity of single-mode fiber, and it can transmit signals of digital, analog, etc. Also network capacity is expanded, so WDM is used in 5G. While using fiber as a mode of propagation, there arise nonlinearities. The nonlinearities are of 2 categories. Inelastic scattering and refractive index effect are the types of nonlinearities. The scattering is due to the light in the medium made of silicon of optical fiber when it impinges on the molecule inside the fiber. There are 2 types in it, known as SRS and SBS. The refractive index is due to the bending of light while it passes from one medium to another. The refractive index effect will lead to FWM, XPM, and SPM. In 5G, as the number of channels increases, these effects become more prevalent. This paper aims to reduce those nonlinear effects such as FWM and SRS that occur in fiber while transmission of signals. 2. Four-wave mixing. Four-wave mixing is a prevailing nonlinearity of in 5G. FWM is an intermodulation phenomenon due to the refractive index effect, as it is the mixing of 3 input waves and forming a new 4th interfering output wave, The new terms that lie near the wanted wavelength can be removed using a filter, but when the new terms coincide with the wanted wavelength it cannot be removed using the filter, so they are considered as interfering terms. Such interfering FWM terms can cause crosstalk, decrease power efficiency. To remove such interfering FWM terms several techniques is used. The FWM equation is .fwm equals .I plus .j-k, 1. The FWM terms are found by using a formula. 3-2. No of FWM terms equals 2. When the input signal is fed into a fiber, it can mix and form new terms of the different and same wavelengths which are given by equation 1, and the number of new terms that arises is given by equation 2, n is the number of channels used. The FWM effect is shown in Figure 1. Fig.1 Spectrum of WDM with FWM terms. The FWM effect is more in equal spacing and more interfering terms appear in the equal spacing technique. To reduce the interfering terms, the unequal spacing technique has been used here. In unequal spacing technique the interfering terms will be reduced and also dispersion will reduce the FWM effect in fiber. This is done for 4-channel and 8-channel using OptiSystem software. 3. Self-phase modulation. The self-phase modulation is nonlinearity due to the refractive index effect. It means that self-induced phase shift induced while the light is transmitted through the fiber. The SPM will broaden the bandwidth. SPM is said to be the most reach-limiting nonlinear effect of the WDM system. 4. Cross-phase modulation. The cross-phase modulation occurs due to the nonlinear refractive index based on the intensity of the beam. It will result in spectral broadening and Burr will increase. V. Stimulated Raman scattering. The stimulated Raman scattering is one of the inelastic scattering effects, which was considered to be nonlinearity in fiber transmission. The SRS behaves incoherently and thus it is unpredictable and dangerous. The SRS effects occur due to the inelastic scattering. Energy is transferred from shorter wavelengths to higher wavelength channels, if two channels have the same power. The inelastic scattering is the incoherent or random movement of the photon to impinge on the molecules of fiber and to lose its energy. In the SRS effect, the power gets transferred to the later wavelength which leads to the power loss in one channel and additional power gain in another channel. PM, K, equals PT, K, power transferred to higher channel, K, plus power coming from the lower channel, K, 3. Where PT, K, equals power transmitted to the KTH channel. The equation, 3, gives the amount of power transferred to KTH. Channel.Fig.2 shows the SRS effect while transmitting through fiber in optical communication for 5G. Equation, 4. Gives the threshold optical power at which SRS effect is being started. 16. PTH equals 4. Where PTH equals threshold optical power in watts EF equals effective area of the fiber core in M2 left equals effective length of the fiber in meter GR equals Raman gain coefficient in cm/watt. The SRS will induce crosstalk and it increases as the length of the transmission fiber increases. To reduce the SRS effect dispersion can be applied up to a certain level. 6. Simulated Brillouin scattering. The SBS is a nonlinear phenomenon that is considered to be in terms of 3 waves in fiber. The incident wave will propagate through fiber reaches the threshold power will excite an acoustic effect and this is unavoidable. This will change the characteristic as fiber including refractive index that makes reflecting waves to propagate in opposite direction. The SBS will cause crosstalk, attenuation, and power saturation. 7. Method proposed. To reduce the 4-wave mixing, FWM, unequal channel spacing technique is used to reduce the interfering terms. The Figure 3 shows the equal spacing. Here it has some interfering terms along with the wanted wavelengths. The wavelengths used here are 1550 nanometers, 1551 nanometers, and 1552 nm. These wavelengths are used as the fiber used here is the single-mode fiber. The figure 4 shows the unequal spacing technique. Here, the FWM terms are not coinciding with the original wanted wavelengths. Fig.4 output spectrum of FWM for unequal spacing. SRS will be reduced using the dispersion. There are two types of dispersion called intermodal and intramodal dispersion. The intermodal dispersion is also known as modal dispersion and it occurs only in multimode fiber. The intramodal dispersion occurs in both single and multimode fiber. It is chromatic dispersion and it is used here. When dispersion is applied, the power tilt will be reduced. If the dispersion is more, that will lead to inter-symbol interference, which in turn increase the bit error rate. The figure 5 shows the SRS effect for 4 channels. The power tilt is calculated between the first and the fourth channel. The power for the fourth channel is 600 MW and the power for first channel is 400 MW. So, the power tilt is 200 MW. The figure 6 shows the reduced SRS effect after including dispersion of 4 ps/nm/km here. The power for the fourth channel is 570 MW and the power for first channel is 450 MW. So, the power tilt is 120 MW. So, the power tilt is reduced up to 80 MW. While going beyond 4 ps/nm/km, it leads to inter-symbol interference, which in turn increases bit error rate. Fig.8 output spectrum for 8-channel SRS with dispersion. The figure 7 shows the SRS effect for 8 channels. Here, the power for the 8th channel is 190 MW and the power for first channel is 80 MW. So, the power tilt is 110 MW. The figure 8 shows the reduced SRS effect after including dispersion of 2 ps/nm/km here. The power for the 8th channel is 175 MW and the power for first channel is 90 MW. So, the power tilt is 85 MW. So, the power tilt is reduced up to 25 MW. The SBS will be eliminated slightly by using low power channels than the SBS threshold, and SBS is not more dangerous in WDM system as it will not create any crosstalk or attenuation. The unequal spacing with dispersion is a combating technique used to efficiently reduce the FWM and SRS effects in the fiber. Fig.10 output spectrum for 8-channel SRS with unequal spacing and dispersion. The figure 10 shows the technique of unequal spacing and dispersion for 8 channels. The power of 8th channel is 295 MW and the power of first channel is 230 MW. So, the power tilt is 65 MW. So, here the power tilt has been reduced much as compared to equal and unequal spacing techniques. So, unequal spacing with dispersion is an efficient technique for reducing SRS. Fig.11 output spectrum showing FWM terms for unequal spacing with dispersion. The FWM effect in the unequal spacing and dispersion technique as in figure 11 is reduced more compared to the unequal spacing technique alone as in fig 4. The dispersion of 5 ps/nm/km is used for the reduction of FWM effect. 8 Table 1, 4 wave mixing terms for different spacing. Technique used no of FWM terms. Equal spacing 9. Unequal spacing 7. Unequal spacing with dispersion 4. Table 2, comparing the power tilt of SRS effect. Method used number of channels power tilt without dispersion, MW, power tilt with dispersion, MW, comparison of power tilt, MW. Equal for 200 120 80. Spacing 8 110 85 25. Unequal for 195 90 105. Spacing 8 180 65 115. 9 Result and analysis. The nonlinearities that reduce the efficiency of the 5G are reduced by the unequal spacing and dispersion in the WDM system. From the above table, it is seen that unequal spacing with dispersion method has reduced more FWM terms and also power tilt is more reduced in this technique. When the two techniques were combined, the power tilt is reduced and the amount of dispersion is also reduced for the SRS effect and the FWM terms are minimized. The channels with power less than SBS threshold power value will also reduce the SBS effect. Conclusion. The effect of unequal channel spacing and dispersion on SRS and FWM are simultaneously analyzed for WDM systems by OptiSystem layout. The variation of power tilt is compared for 4 and 8 channel WDM system for equal, unequal, and unequal channel spacing with dispersion. As unequal channel spacing and dispersion are combined to mitigate the effect of SRS and FWM simultaneously, dispersion process makes the signal to undergo pulse broadening at the initial stage of signal transmission through the fiber. So, the future work is implemented by overcoming this pulse broadening and transmitting the signal with large number of channels in fiber optic WDM systems.